Alright, so in this video we're going to discuss the linked list data structure. We're actually going to be talking about the singly linked list data structure. So list is in the name, so it's sort of like a Python list. It does not have nearly the functionality of a Python list, but it's a way of storing multiple values. Alright, and so we're trying to understand how the computer can do some of this stuff for us, and it helps to create these data structures ourselves from scratch and create a bunch of different ones, start understanding how data structures work. So we're going to create a file called node with a capital N.py. So we are going to be making use of classes in this video. If you're unfamiliar with classes, just simple classes, but you should know a little something about them. Alright, so we're going to create a class node. Now notice I named the file with a capital N because the primary export of this file is this class node. Alright, so we have a class node, and then we define the constructor or the init function. Alright, and this object is going to have a very simple structure. We have self.value. That's the actual value each one of these nodes holds. Right, and we're going to get that from the constructor. So when we create one of these node objects, we'll pass in that value, and we'll set it. We'll attach that to our object. So here, self is this. We get this parameter. We have access to self, which is the object itself. It's the object that's being created. This parameter self is automatically provided to this init function by Python when you instantiate the class. Okay, I'll show you what I mean here in just a second. So we'll actually just leave it right here. This is about as simple of a class as you can have. We have one function, the init function. Most classes are going to have an init function, and we are setting one property, attaching one attribute to our object, right? And we get that from the constructor. And then once we attach it, then we return the object. Okay, so if you've seen this syntax before, this is sort of a nice trick. The __ name variable in the global scope of a file is built into Python, and if it's set equal to __ main, that string value, then that means this file was run directly. It wasn't imported by another program. So this is sort of a nice quick way to test your code, and it's only going to run if you run the file directly. This test code won't run if I say import this file into another. Okay, so this is just a sort of quick and dirty way to test some things. Alright, so what we want to do here is I want to create one of these nodes. So node 1, I'm going to say, is a node. Okay, now this is the class name. Notice it's capitalized. Classes by convention are capitalized in Python, and I'm going to pass in the value associated with this node. So this can be anything. I'm gonna say it's a cat. All right. Now, notice when I call this class, by default, Python automatically invokes the init function. Also, it creates a simple object and then passes that in as the first parameter or first argument. So self becomes, the self parameter here becomes a simple brand new object that has all of the default properties of an object in Python, and then you can add your own here, which is what we do. So value here, that parameter is actually the first argument we provide to the class. Okay, so we don't have to provide this one. Python provides that. So all of your class methods are going to have, your instance methods are going to have this self function or this self parameter, right? But you won't actually have to provide that. That self is always going to be provided by Python automatically. That's the way the class structure is designed in Python. And so this is going to reference the object itself. Okay, so in this case, it's just one of these nodes, and this node happens to have the value cat, so that gets passed in there. And then we attach a property or an attribute called value. We set that equal to what was passed in here. Right? And these names don't necessarily have to be the same thing. Right? these two do have to be the same, right? But this is the attribute that's actually attached to the object. Okay, so for all practical purposes, this is just like a function. This is any other function parameter. It's essentially a variable name, and you can name that whatever you want. But here is where we're setting the attribute that's actually attached to the object. Okay, so here we can say print, and I want to print out in1 dot value. So notice I have to say dot value because that's the name of the attribute. Right? I can't say val. And so I can save this and I can run this Python 3 node. All right, and we see that node just has a value cat. All right, so we're going to add one more thing to this, very tiny distinction. So self dot, and then we're going to have a next property. And we're going to set that equal to none. Hopefully you're familiar with what none is. It's essentially a way to define an attribute but assign it no value. Okay, so none is sort of like undefined in JavaScript. It is no value, right? We can't use 0, like the number 0, because that is a value, right? Even though the number 0 represents nothing, that's still a value, right? So the idea here is this: it's an abstract concept that we have a variable, or in this case an attribute attached to an object that has no value. All right, but what we want to do here is we want to make several nodes and we want to try to connect them together. Okay, so if I have in1 here is a cat and I have in2 is dog, we can print into dot value. All right, we've got cat and dog. So these nodes are basically containers that are holding the value that we're interested in, right? So just like in a list, in a Python list, it's a collection of values. So we're just creating a programmatic way of encapsulating the data that we're interested in some sort of class structure. Okay, so the value is the actual thing that we're wanting to store, but we need some mechanism that we can link all of these nodes together, right? So one of the ideas behind a Python list is it's a collection of objects. One object comes before another or after another, right? So there's an implied order, right? One and then the next and then the next and then the next. This is an iterable, and you can iterate from one item to the next item to the next item to the next item. Okay, so we want to set something up that's sort of like that. All right, we're going to do that with this self.next property. So let's make a couple more nodes. I'm just going to copy and paste to make this a little bit quicker. So we have N2 and N3. Okay, we have 3 nodes. And I'm going to add a little break here. So what I want to do is I want to connect them together. So I can say N1 has the next property, and I'm going to set this equal to something else. What am I going to set this equal to? I'm going to set this equal to N2. All right, so something that's important we need to discuss is sort of how identifiers get the values associated with them, right? So this is an attribute on an object. It's really just you can think of it like a variable or another identifier. It's an identifier that's attached to this object. So this identifier is really storing a memory location, right? So that's how all of this works in Python. Variables actually hold memory locations, an address in memory. Python looks in that address to find something. And it finds a blob of binary data. That binary data tells Python what type of data you're dealing with and also the value associated with that data. Okay, so in this case, Python goes to the memory location of value, right? And it goes and finds what's there, and it turns out to be the string cat, right? So here, what we're doing is self.next. This is an identifier, right? It's an attribute attached to this object. It's basically just a memory location, right? It's a memory address. So what's stored at that memory address? Well, the same thing that is stored in this variable, right? N2, right? So by doing this, the node in1 has a next property, and that next property I'm setting it equal to in2, right? But that's sort of not exactly true. What I'm setting next equal to is the memory location of this data. Okay, so I'm not creating two separate pieces of data. There's still only one in2 node, right? And I can sort of prove that. I can print out the ID of node 2, and that's essentially the memory location, and I can print out the ID of in1.next. Okay, so that's all we're doing. We're printing out the memory location of these two items. Remember, this is just an identifier, in2, so it's pointing to a memory location, which points to the actual value of in2. It points to a big blob of data in memory that has a type. The type of that data is node, right? That node has these attributes, right, that also have memory locations. All right, so that's what's happening memory-wise. Now let's run this real quick. Okay, so these are the IDs. All right, so it's effectively the memory location. Notice that they are exactly the same, right? So that means the value that's stored in in2 is the exact same value that's stored in in1.next. Okay, they are the same object. Okay, there's not two separate objects, right? So what I've done here is in1 now has a way to access in2. So it can do that from its self.next property, right? So in1.next is going to point to in2 because we set that up here. All right. Now another point of distinction or point to clarify about classes is this self property. It's always the object. It's not always the same object. It's one of the objects that was created with the node instantiation, right? So in2 we created a node. This is a different node than in1, right? So whenever I say, so here for example I say in1.next, this in1 is self, right? So self.value in this case for in1 is going to be the value cat. That would be a different value if I used one of these other nodes. Okay, these other nodes have different IDs, right? So what is the ID of node 1 and what is the ID of node 2? Oh, we already did node 2 up there, so we're going to do node 3. Right? So these are all nodes. We see again that these two have the same memory location, right? And it's different from the last time we ran it because the program stored this in a different place when we ran it this time, and that's fine. But we see the first two are the same, right? That is in2, which is the identifier, or just the variable. It's the identifier in the main scope of the program. And then in1.next is the attribute on the in1 node that points to that same data. So those two are the same. And then in1 is still a node, but it's a different node that's storing a different value. It could potentially store the same value, but in this case it's still a different node either way. All right, so it's a different blob of data in memory. And then in3 is also has a different ID, so it's a different blob of data. Okay, so back to linking these items together. So here I have linked in1 to in2, and then I can say in2.next equals in3. Okay, so what I've done here is I've effectively created a chain or a linked list. These are all linked together now. Okay, so what I can say here is if I start with an initial node and set that equal to in1, right, I could say while node does not equal none, I'm going to print out node.value, and then say node equals node.next. Okay, so this is a relatively simple piece of code. We start out with some identifier node and we set it equal to one of our nodes, right? Now because we link them in a specific way. 1 links to 2, 2 links to 3, right? Because of the way we link them together, we can do this behavior where we loop, and as long as that variable node does not point to, right, it's not equal to the none value, right? We'll print out that node's value, and then we'll set that variable node equal to node.next, which would be the next node. Right? So if we run this, we'll take a peek, and we see we've iterated over each one of these items. With this little bit of code, this is effectively iterating over a linked list. Now we created the linked list manually here. We manually made these connections. in1.next equals in2, in2.next equals in3. Right? So this is a singly linked list, sort of. Right? It's actually just connecting the nodes. What we want to do is we want to make another file that is a singly linked list, and it imports this node class, and it uses this node class, and then we'll have a singly linked list that basically wires up these connections for you anytime you add an item. Okay? So we won't have to do this manually like this. Now one thing we should be aware of is the efficiency of this. So the idea of a singly linked list, if I want to access the first item in our list, if I only have access to in1, then it's constant time to grab the first item in the list. I just look up the property in1.value. If I want to find the last item in our list, I have to look up in1.next, and then that values.next, and then that nodes.value property, right? So we'll talk a little bit more about that after we make the singly linked list program, but we have to think about the efficiency and how long it takes, how much work does it take to access an item, specifically the last item in a singly linked list. All right, so let's do that. Let's create a new file called singly linked list, or single linked list.py. Okay, and move that open just a little bit. And here we're going to, from the node package here, so this is the package name, we're going to import one of the items that's defined in this package, and that's this class node. Okay, so from node, which is the package name, import the specific item in that package, which is the node class. So now we can use a node in our file, and we're going to make this a single linked list. I'm going to define the init function. I have the self property. We're going to pass on this. And then we have name is main. Alright, so this will just, when we run this program, it's just going to print out testing and then the name of the file. So we want to run Python 3 single linked list. Alright, so it's testing single linked list.py. Alright, so what goes into this single linked list? Well, to start with, we need a starting point. We need a self.start. We need some value, and that should be a node. Okay, but what if we have an empty list? Well, if we have an empty list, then there is no node to start with, right? Remember, the nodes basically encapsulate one of the values. So if I don't have any nodes, that just means I have an empty list. We see that all the time in Python with a list, with the list data structure. If the length of the list is 0, then there are no items in your list, right? So that brings us to another point. We probably want to have a length. And we can set the length equal to 0 to start with. All right, so that's simple enough. So first thing we need to do is be able to add things to our singly linked list, right? So we can define add, and remember we pass in the self parameter, and Python automatically will pass that in when we reference when I reference the singly linked list that I've created. So all of your instance methods need that as the first parameter, even though you never specifically pass it in yourself. Python does that for you. So adding an item to our collection. Well, what do we want to add? We don't know. It's whatever the user specifies. So that's basically the data, the item that the user wants to add to the list, right? And what we want to do first is we want to create a node with that data. So I'm going to create one of these nodes, right? And remember, what are the properties on a node? What are the attributes? Well, it's just value and next. And by default, next is the none value, right? So this node doesn't link to anything, right? But it does have the value, and that value is whatever the user passed into the add function. Okay. So we have to think of any special cases. All right. So if self.length is 0, that means we have no items in our list. Okay, so that means the very first item in our list is going to be this new node, right? Previously, the start of our list pointed to no nodes. There were no nodes, right? Now we have one. So we're adding an item. If the length is equal to 0, it means there's no items in our list. So we set self.start equal to that node. Then what do we need to do? Well, we now have an item in our list. So we have to say self.length plus equals 1. All right. And then what? Well, that's enough. We just return because we have successfully added a node to our linked list. All right, so let's try out our functionality here. We have a linked list is equal to a single linked list, and then our linked list dot add. We're going to add cat, and then I can print out linked list dot start dot value. Okay, so the linked list has an attribute start, which points to a memory location. That memory location is holding a node. So this is essentially that first node that we've added, right? And then dot value is a property on that node, which is basically a memory location. It's a memory address. And when Python goes and looks in memory at that address, you have a value stored, and that should be whatever we passed in to add. Because remember, add has this item, right? So this string is this item. It's not self. So remember, with classes, it's one thing that's confusing. We never have to pass in this self. That self is whatever object we're referencing back here. So in this case, this self is this linked list. So when I have an object dot, that is the thing that's always passed in as self. So it's this particular linked list is self in this case. And I called add with this string, so that is the item. And if I had other things here, right? If I did something like this, this number 4 would be the NUM parameter, right? Okay, just as an example. So anyway, we have we passed in cat here for item. We created a new node using that item, so which is cat. And so we have this node that's holding the value cat. If the length of our list is 0, which it is, then we set self.start equal to the node. Right? So this ll.start should equal, or should effectively be, the memory location that points to our node, and then that node has a attribute value that is a memory location that points back to cat. All right, so let's run this, and sure enough, there we have cat. All right, what happens if we want to add another item? ll.add dog. Well, ideally, we would have the linked list, and we could go to .start, and then that is the first node, and we'd have another node attached to the next property, and then that node would have a value of dog. Right? Now, this is not going to work because we haven't added that functionality. The only way we can add right now is if the length of our list is 0. Right? So if we run this, we're going to get an error. Right? So what we have to do is we have to add in that functionality. So this was the special case if the length was 0. Right? And then this is going to be the rest of the cases, right? So we want to start out with a node, and we know we have a node at self.start. We know that for a fact because if we didn't, we'd be in this case, right? This is the code that would run if we had no items in our list. So we know there is one node at self.start, right? And so while let's see, node while node.next does not equal none, we're going to say node equals node.next. Okay, so this code is similar. It's not exactly the same, but it's similar to in our node program. Back here we had this code with the while loop. It's a little bit different because I'm not, instead of checking the node identifier itself, I'm checking node.next. Now the reason for that is because I need to have a node in here. I can't have a value none because I'm trying to get the last node in this list, and then to attach it I have to set that node's .next property to our new node. Right? So here's our new node. Right? And I'm reusing the variable here, so I need to fix this a little bit. I'm going to say new node, new underscore node, and here this is new underscore node. Right? So the new node is the new thing that I've created. Right? I've got a new node here. I've got the item in there. So if length is 0, self.start is that new node. Down here, node is just some generic node, and we started out with self.start. The purpose of this is to find the last node in the list. Okay, all of these nodes are linked together with the .next property. So node.next, .next, 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 .next. The way we find the last one is if node.next is equal to none, because by default all of the node values or all of the node.next attributes are set to none. The only time we ever set node.next is in singly linked list, and that's what we're doing on an add. Right? So we want to find the last item in the list, and this accomplishes that. So at this point, node should be the last item in the list. And if it is, then we say node.next is equal to our new node. And then we can say self.length plus equals 1. All right. So let's imagine that this is the second scenario. We've already added one item, and that takes care of this. Then we return, right? And then we go down here and we add dog. Okay, so dog is item. We create a new node with dog. Is the length of our list 0? No, we already have one item in it, so the length of our list is 1, so we skip down here. Node is the start of our list. So this is a node that holds cat. That's what this is initially. So while node.next does not equal none, well, in this case it does, so we don't run this at all. We skip out of the loop. Node.next, that original node is our cat node, and we haven't set a .next property for it, so it is none. So this is a false statement. And so we break out, and we say node.next then, so node is the cat node still. We're now going to say node.next is our new node, which is our dog node. And then we add 1 to the list. And so down here we'll see we have a linked list, the starting node, next will be the dog node, and then you get the value of the dog node. Cat, dog. So we'll try one more case to make sure this is working. We're going to pass in bird. So we have linked list.start, that's going to be the cat node. .next is going to be the dog node, and then .next should be this new bird node. And then the value will be the string bird itself. All right, so let's imagine what's going to happen here when we're adding bird. We add in an item there, bird, and we create a new node. So node has a dot value of bird. Is the length of the linked list 0? No, we already have 2 items in it. So now node here is going to be the start of our list. So this is the cat node. Does node.next not equal none? That is correct. It does not equal none because we do have a value, node.next. Node.next is the dog node. Okay? So now we set this identifier, which was cat, the cat node. We're setting that identifier to the dog node, right? Because remember, node.next, here node is the cat node still. Cat node.next, this whole thing is the dog node. And so we're changing the value of node to be the dog node. All right? On the right-hand side of the assignment statement, this node is still the old value. So this expression has to be evaluated, and then it gets stored as the new value of node. So everything to the right here, node is still the old cat value, right? Node.next, and node.next is the dog node. So the dog node now gets stored in this identifier. So then, does dog node.next not equal none? This is false. It does equal none. So then we take the dog node dot next and set it equal to our new bird node, and then we add 1 to our list. Okay, so there's not really much going on in this code, but it is a little, you have to really take your time with it and examine what's happening, right? There's really not that much to it, but we're just adding things together and linking them together. This is the linked list. We have a starting node, then a .next, and I could have 100 different values in here. I could say for I in range 100, and then I could say linked list.add, and I can add an item, I, and I can print out linked list.length, and I can print out linked list.start, next, 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 value. And I could keep going because I have 103 items in the list now, right? So we could run this, and we have bird. The length of the list is 103. Length list.start is the cat node. .next will be the dog node. .next will be the bird node. This will be the number 0 from this range. We added I equals 0, and then this would be the number 1 node, and we get the value, and it's the number 1. Okay, so that's adding things to a linked list. Now, how do we get something from a linked list, right? Well, this is pretty tedious, right? I might want to get something by an index number, right? So we could say define get, and we pass in an index. All right, so whatever that index is, if index is greater than or equal to self.length, then we can print an error out of bounds or something like that. You know, we might want to create an exception and throw it. That's a little bit more than I want to get into for this video. But so we print error out of bounds, and then we could either just return none, which that might be something you want to do, but then that could get confusing because perhaps you stored the value none in the list, which you can do in Python. I can make a list and have a none value and then cat, right? So it can get a little confusing doing that, but we're just going to do that for the sake of simplicity now. So if the index is out of bounds, we print a statement that says error out of bounds, and then we just return none. So that might not be the best design decision, but that's what we're going to do here. Okay, so if the index is greater than or equal to the length, right? And also, we can say it or the index is less than 0. Right? So it would be nice to do negative indexing, but we're not going to implement that yet. But Python has a really nice strategy for negative indexing. It's pretty helpful. So that might be something we want to, you know, employ. We might want to add that functionality at some point. But this would be where you would do that. All right. So we've handled all of the cases where we have an invalid index. So now we know that the index should be referencing something in our list, right? If it was bigger than the length, then there would be no node that we could access with this index. If it's smaller than 0, then there's no node associated with that index. So whatever the index is, we need to keep track. We say we start at count 0, right? And then we say node equals linked list, you know, self.start. Right? And also, this is my fault, I forgot to add in our self parameter. Remember, so we're adding a function to a class. This is a method of the class, and you always have that self parameter as the first parameter to your function, right? So I left that off there. But we're never actually going to provide that, right? Python provides that itself. So we are going to provide the index number. So we're going to try to get a value of the node at this index. All right, so the reason I had to make sure I had self in there is because I'm accessing self.start, which is the very first node in our linked list. So I need to have that self parameter in there. So self equals self.start. So we're trying to find the node that matches index. So we can say while index is bigger than count, then we're going to say node equals node dot next, and then we're also going to increment count. Count plus equals 1. All right, so if we had, 100 nodes and index was 10, we start at the first node, that's the index 0 node. Is 10 greater than or equal to or greater than count? Yes. So we get the next node, add 1 to count. Is 10 greater than 1? Yes. Is it greater than 2? Yes. 3, 4, 5. Until we get, is 10 greater than 10? No, it is not. Right? So at that point, node should be the 11th item in the list, or the index 10 node. Right? And so then we would return node.value. Okay? And that's all there is. But notice we keep using this sort of style. This is how you iterate through your linked list. Node equals, and then self.start, and then you have a loop, and you try to find the last element in the list. All right, so we'll get an item, and what we could say here is we're going to print out linked list.get the item at index 0, right, which is effectively the same as this. All right, we'll duplicate this line and move it down. Here we'll get the item at index 1, right? So this is the node at index 0, this is the node at index 1, and then we get the value, right? So these should match. So this would be item at index 2, and then we would go down here, and so this would be the item at index 0, 1, 2, 3, 4. So this should be get 4. Cat, cat, dog, dog, bird, bird. That's the length of the list, 1, 1. Okay, there's not an incredible amount going on here, but it is complicated. Right? So you should be able to code this up for yourself and make sure you understand the steps. And you can add all sorts of other things to this, right? You could add removing items, popping items by index. You could find an item by a value. You could remove an item by a value. There's all sorts of functionality. Think about all the functionality associated with the Python list. All of that you could do here. Now there's one important aspect of this that should be discussed before we end here, and that is the efficiency of this function get. All right, if I want to get the last item, we need to talk about efficiency in terms of how many cycles, how much work does it take to do something, right? Algorithmic work. This gets into big O notation and time efficiency. I don't want to go too in depth here, but we're just going to do a simple little example. I'm going to say work equals 0, right? To start with, we'll start it at 1, okay? And then if each time through this loop, let's move this down a little bit. So work 1, we're saying 1 unit of work is if we grab self.start, right? That's accessing an attribute on our object, and that's a memory location, and that memory location, we have to look up what's in that memory location. So we're going to call that 1 unit of work, looking up something in a memory location. All right, and then down here, inside this loop, each time we iterate through this loop, we have to do that 1 unit of work, right? We have to access something, right? We have to access that object's next property, which is a memory location, and then go get that item, right? So instead of work equals 1, we're going to add 1 unit of work each time through this loop. So we start out with 1 unit of work, and we say that's accessing an item. And then here's another unit of work. And we're going to ignore this count, right? That could be a unit of work as well, but we're just going to ignore that for now. The point that I want to get at here is at the end, we're going to print out how much work has taken place. All right. And so anytime we call get, we're going to see how much work has taken place. And then down here, I'm going to print out ll.get, and I'm going to get the item at index 100. Okay, so each one of these get calls is going to print out the amount of work that it took to get that value. Okay, so getting the first value is simple. We only access one property, so very simple. So to access the first one, easy. Work is just 1. Access the second one, well, work's a little bit more. And each item in a linked list, as you progress down the linked list, it takes quite a bit more work, right? So the item at index 100 takes 101 units of work, and 97 is the value. Now remember, that's because we have cat, dog, and bird beforehand, so there are 100 other items beforehand. Right? So 101 units of work. So that means accessing the last item in a linked list is not very efficient, right? The bigger your list is, the longer it takes to access that last item. So it's not a super efficient algorithm necessarily. What it is good for is a stack data structure. A stack data structure, you add items to the start, and then you can remove them from the start as well. We would have to change this a little bit, how we add items, because right now we're adding items by node.next. We're adding to the right from the right hand side, right? And so a stack you'd have to remove from the same side, right? But we could change this a little bit so that the self.start is always the latest thing added, right? And if we did that, this would be a good data structure to use to implement a stack. Right? Now this again is a singly linked list. We can have doubly linked lists that have a start and an end property, and then also in a doubly linked list we would have a self.previous, and the self.previous would link to the node beforehand. So in a doubly linked list, every node has an attachment to the next node, and every node has an attachment to the previous node. That's something we don't have in a singly linked list. And if you think about that, that would increase or decrease the amount of time it would take to get to the last item. Right? And the last item of the list we could just access with self.end. So really then, in that case, the hard items to get would be the ones in the middle. Right? So anyway, this begins to touch on time complexity and algorithm efficiency, and it's important that you start thinking about algorithm efficiency. How many CPU cycles does it take to do something? Is this efficient? We want things to be efficient so they don't take a lot of compute cycles. So other things that need those compute cycles have them, right? So anyway, this is the basics of a singly linked list in Python 3.